For our practical exam in physics, we are going to discuss a topic about the ideal gas law. The ideal gas law is also known as the general gas equation. It is an equation of state of an ideal gas that relates pressure, volume, quantity of gas, and temperature. While the law describes the behavior of a hypothetical gas, it approximates the behavior of real gases in many situations. The law was first stated by Emile Clapeyron in 1834. The law combines Boyle's law, Avogadro's law, Gay-Lussac's law, and Charles' law. The ideal gas law is expressed by the equation PV is equal to nRT, where P is pressure, V is volume, N is the number of moles of an ideal gas, R is the ideal gas constant, and T is the temperature. The first law that we will discuss is Boyle's law. Boyle's law states that the relation between volume and pressure at constant temperature and mass. Robert Boyle conducted an experiment on gases to study the deviation of its behavior in changed physical conditions. It states that under a constant temperature, when the pressure on a gas increases, its volume decreases. In other words, according to Boyle's law, volume is inversely proportional to pressure when the temperature and the number of molecules are constant. The formula used in this law is P1 times V1 is equal to P2 times V2. This equation will be ideal when working with the problem asking for the initial or final value of pressure or volume of a certain gas when one of the two factors is missing. The second law that we are going to tackle is Charles' law. Jacques Charles in 1787 analyzed the effect of temperature on the volume of a gaseous substance at a constant pressure. He did this analysis to understand the technology behind the hot air balloon flight. According to his findings, at constant pressure and for constant mass, the volume of a gas is directly proportional to the temperature. The formula used in Charles' law is V1 over T1 is equal to V2 over T2, where V1 is volume 1 and T1 is temperature 1, and V2 is volume 2 and T2 is temperature 2. This equation can be used to solve for initial or final value of volume or temperature under the given condition that pressure and the number of mole of the gas stay the same. The Gay-Lussac's law, also referred as pressure-temperature law. The Gay-Lussac's law was discovered in 1802 by a French scientist, Joseph-Louis Gay-Lussac. While building an air thermometer, Gay-Lussac accidentally discovered that at fixed volume and mass of a gas, the pressure of that gas is directly proportional to the temperature. The temperature here is measured on the Kelvin scale. The graph for the Gay-Lussac's law is called an isochore because the volume here is constant. The formula that is used in this law is P1 over T1 is equal to P2 over T2. The P stands for pressure and the T stands for temperature. The combined gas law combines the three gas law, Boyle's law, Charles' law, and Gay-Lussac's law. It states that the ratio of the product of pressure and volume and the absolute temperature of a gas is equal to a constant. When Avogadro's law is added to the combined gas law, the ideal gas law results. Unlike the named gas law, the combined gas law doesn't have an official discoverer. It is simply a combination of the other gas law that works when everything except temperature, pressure, and volume are held constant. There are a couple of common equations for writing the combined gas law. The classic law relates Boyle's law and Charles' law to state PV over T is equal to K, where P is equal to pressure, V is equal to volume, T is equal to absolute temperature, Kelvin, and K is equal to constant. The constant K is a true constant if the number of moles of the gas doesn't change, otherwise it varies. Another common formula for the combined gas law relates before and after conditions of a gas. P1 V1 is over T1 is equal to P2 V2 over T2. The last and final law that we are going to tackle is Avogadro's law. Amadeo Avogadro in 1811 combined the conclusion of Dalton's atomic theory and Gay-Lussac's law to give another important gas law called Avogadro's law. According to Avogadro's law, at constant temperature and pressure, the volume of all gases constitute an equal number of molecules. In other words, this implies that in unchanged condition of temperature and pressure, the volume of any gas is directly proportional to the number of molecules of that gas. Volume of a gas is directly proportional to the amount of gas at a constant temperature and pressure. It is expressed in the formula V1 over N1 is equal to V2 over N2.
In this section, I'll be showing to you the application of these gas laws in our everyday life. Boyle's law. You can observe a real-life application of Boyle's law when you fill your bike tires with air. When you pump air into a tire, the gas molecules inside the tire gets compressed and packed close together. This increases the pressure of the gas, and it starts to push against the walls of the tire. You can feel how the tire becomes pressurized and tighter. Charles' law finds its way into our kitchens as well. In case you have ever tried your hand at baking, you might be familiar with the substance most commonly used in cooking, the yeast. Yeast is often used in baking to make the bakery products fluffy. Yeast is responsible for releasing carbon dioxide bubbles. These carbon dioxide bubbles expand further with high temperature. The expansion of the carbon dioxide bubbles with an increase in temperature works as a leavening agent and causes the bakery products to become fluffy. The pressure cooker is a sealed utensil for cooking food under steam pressure. It is usually made of steel or aluminum. When heat is supplied, the water inside the cooker vaporizes, and the steam is produced. The steam is periodically released through a valve to maintain the operating pressure inside the cooker. For Avogadro's law, human lungs demonstrate Avogadro's law in the best possible way. When we inhale, the lungs expand because they get filled with air. Similarly, while exhaling, the lungs let the air out and shrink in size. The change in volume can be clearly observed, which is proportional to the amount or to the number of molecules of air contained by the lungs. One example of the combined gas law applies to scuba diving. In scuba divers, human lungs are the container that holds the gas. The pressure in water is greater than pressure in air, and water pressure increases with depth. With each additional foot that divers descend, water pressure rises. Therefore, divers must take adjustments to maintain the proper pressure balance between the lungs and the water. This change must also take place gradually to create an equilibrium. If a diver with full lungs ascends rapidly on a warm day, the volume of the air in the lungs can expand quickly. Therefore, he or she must exhale quickly to allow gas in the lungs to escape. For the last example, ideal gas laws are used for the working of airbags in vehicles. When airbags are deployed, they are quickly filled with different gases that inflate them. The airbags are filled with nitrogen gases as they inflate. Through a reaction with a substance known as sodium acid, the nitrogen gas is produced, while sodium metal undergoes a reaction with potassium nitrate, neutralizing the sodium, and enough gas is produced such that the airbag is inflated but not overfilled.
So now let's solve this problem. So we have a 60.0 liters balloon is filled with air at sea level, 2.00 atm and 45.0 degrees Celsius. It's tied to a rock and thrown in a cold body of water, and it sinks to the point where the temperature is 6.0 degrees Celsius and the pressure is 13.00 atm. Now, what will be its new volume? So, first let's look for the variables we have. So for the first variable, is initial velocity is equals to 60.0 liters. Initial pressure is equals to 2.00 atm. Initial temperature is equals to 45.0 degrees Celsius. Final temperature is equals to 6.0 degrees Celsius, and lastly, final pressure is equals to 13.00 atm. So from this, we can see that we have velocity, pressure, and temperature. From here, we can conclude that we will be using the combined gas law to solve this problem. So the formula for combined gas law is P1 V1 over P1 is equals to P2 V2 over P2. So from here, let's check the given. We have initial velocity, initial temperature, initial pressure and initial temperature, final temperature, and final pressure. Now, the missing variable is final velocity. Now, what will be the new volume? First thing to do is rearrange the combined gas law so we can solve for the final velocity. Now, final velocity is in this side, so we will multiply both sides by final temperature to get final temperature out of the denominator. Now, let's cancel final temperature here. Now, we can rewrite this as so as you can see, P2 is still with V2. So in order for us to solve for V2, V2 must be alone. So we need to get P2 out of the numerator. What we will do is we will divide both of the equation by P2. Okay, so divide by P2. Now we can cancel the P2 in this side. So from that, we can have our final equation, which is V2 is equals to P2 P1 V1 over P1 times P2. So we have here our given, and our required is final velocity, and our equation is this. Now, before we move on to the solution, we must convert the Celsius of the temperature into Kelvin by adding the Celsius by 273 Kelvin. So, 45 degrees Celsius plus 273 will be equals to 318 Kelvin. And 6.0 degrees Celsius plus 273 is equals to 279 Kelvin. So now for the solution, we will just have to substitute all the given. So V2 is equals to, for the final temperature is 279 Kelvin. Initial temperature is 2.00 atm, and initial velocity is 60.0 liters over initial temperature is 380 Kelvin times final pressure is 13.00 atm. So for the last step, we just have to input all of this in our calculator and we will have our final answer. So 279 times 2 times 60.0 liters divided by 380 Kelvin times 13.00 atm. So we have 8.099. So our V2 is 8.099. So for the unit is cancel Kelvin, cancel atm, and our unit will be liters. So our final answer is this. The value of our missing variable, which is final velocity, is equals to 8.099 liters. And that's it. That's how you solve this problem.
In conclusion, the gas laws are usually included in our everyday life. We could be in the gas station pumping the gas or baking in the kitchen. The introduction was made by Joanna Cablitas, The second part about the gas laws involving our everyday life was made by Kyla Balahaja, Shakira Concha, who answered a certain question about gas law, and Kiana Janea, who edited the video. Thank you for watching and God bless.